पीछे से पीछे पीछे से सबको चेंज करना है। अच्छा इसमें इस साइड वालों से शुरू करें शुरू करें Good afternoon. So today we have Dr. Somnath Bar here. Dr. Somnath Bar, Dr. Somnath Bar is a geospatial and earth observation researcher scholar, and with 8 year experience, he is currently a postdoctoral fellow at University of California, USA. Dr. Somnath Bar holds a PhD in geoinformatics, focusing on Himalayan forest fire and their role in forest degradation and regional atmospheric pollution. His research explore the increased interaction between the land and atmosphere, contributing to a deeper understanding of long-term climate change. Before joining the University of California, Dr. War worked on the vegetation remote sensing project at University of Southampton, UK, where Dr. War contributed to the development of fine scale vegetation product using the Sentinel-2 data from the European Space Agency. He also played a key role in validating the yeah validating the Copenhagen land vegetation project. Dr. was as authored in several international reputed journal papers, and some of his research work is well featured in the Physics or Science magazine. His research advanced Earth observation science by developing innovative methodologies for the studying environmental change, ultimately the supporting more effective in climate adaptation and mitigation strategy. So today he is going to talk about the Indian forest fire dynamics and potential scope in fuel management. He will talk about the special temporal pattern of the forest fire across the India and their links in environmental and human factors. So I welcome Dr. Var here. So Dr. Var, now over it's you. Hi. Can you hear me? But wondering about the online people. I make it on. I make it on. Here. Yeah. I believe online people also can hear me. Thanks, Dr. Dumka and Aries for inviting me and having me here for this talk. And it's really, interesting to do a visit at Uttarakhand because it was my study area. And I've been in 2019-20 doing field work, roaming around the Uttarakhand from north to south, east to west. Uh, and I started from 2018, and after that completed my PhD on 2022 and moved to University of Southampton, then University of California. So mostly it was around vegetation, forest fire, all those things are there. So I'll try to offer a story of Indian forest fire dynamics, compiling a few of my research work that I published since last few years. Uh, uh, let's uh, let's let's say what are the outline or content that I have today is what are the connecting dots to understand the Indian forest fire, and how about the fire spreading mechanism, then fire window and seasonality about the Himalayan as well as the inter-Indian fire, then special intensity or size of the fire spot, and then burn area and all, and then fire relative power and connecting the fire occurrence intensity with regional and global climate, then incidence modeling and projection. Then we'll try to go some fire and emission estimations, then forest degradation due to fire, and then how the fuel cycle or climatic cycle is connected together, which really plays a role in deciding that what will be the intensity of fire, what will be the place of fire. Then we'll try to talk about some fuel management techniques following the climatic cycle and fuel cycle. If I say about the the major component which play in forest fire over India, it starts with the good things is that over India we have three major cluster. It's not the not over the entire India. If I say the three cluster is from north, south, and to the central, and some parts of the east. And what another key important component is the fuel type or the vegetation type, that is plant functional type. And if I say in India, we have around 55% of the forest or vegetations are deciduous forest, and that's one of the main fire prone vegetation, and which has a seasonality. It has a phenology of peak and down. And while down, you will get lots of leaf litters, and which is the one of the immediate fuel or fine fuel to initiate the fire or the spread the fire. And yeah, so if I say three major zones, it's the central and southern highlands, where you'll find most of the vegetation types is deciduous and sub broadleaf forest are there. And we have north, central and western Himalayas, including Uttarakhand, Himachal Pradesh, and some parts of Nepal and the northeast Himalayas. Uh, yeah, there's a fire point count. I think this slide this content I take from the Reddy et al. 2019, and they found that okay, which are the places like for 1 year, 5 year, 10 years, out of I think 15 years, how many points they got, you know? Okay. Mm-hmm. Mm-hmm. Means the repetition over okay, it's kind of repetition of the fire points. Uh, 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 mm-hmm. Okay. I think it's a total. It's average of 15 years. Sorry, it's not accumulation. It's average. It's average of 15 years. Means in that location, what is the total number of? Sorry, the average number of fire in that 15 years. Mm-hmm. Uh, okay, okay. Okay, maybe I need to check what they're exactly representing it. But my intention was to represent that which is the major cluster of the fire over India. Yeah. It's the grouping means the less fire. That's a no fire. Blue color is a no fire. Okay, okay. Actually, I didn't notice that what that mean, but it seems like a frequency. Yeah. That's an interesting question. What the, um, no. Okay, so this okay, they are using I think BISSR or MODIS data, and it will give you the point of the fire locations, and I think it's in I don't know the grid size what they use. Uh, Probably it's 1 kilometer 1 kilometer grid, and within that grid was the number of. Mhm, mhm. Okay, okay. I think it's the grid count, the number of grid count. It's like if I say a histogram, it's a grid count for total number of 15 fire observed is 1050 grid count. I think it's a grid count. Yeah, it's yeah, it's grid. It's a grid count, means there's a frequency. The grid count is if I say the spatial map, if I put it in a histogram, okay, for 1 year, how many grid counts is there? Yeah, how many grids are there? Yeah, yeah, yeah. Okay, okay. This 1 year means this in that particular location that receive fire for only 1 year out of that 15 years. In the- Okay, the idea is suppose you are you are considering 15th year of observation. Okay. Okay. In terms of the fire spreading mechanism, all over the India is almost it's mostly surface fire, which takes the advantage of the surface fuel, leaf litters, and some sort of grasses to initiate the fire. And there's a global study which recognized that over India, you will find most of the area is or most of the fires are the surface fire with the medium frequency in respect of the global fire intensity. And I was trying to do some fire categorization based on field work over over Uttarakhand, and you'll see the there are few images that you'll see the the deposit of the leaf litters is around 10 to 15 inch that dried leaf, and mostly fires are the surface fire. If you have a good amount of ladders, might be that can help to reach out the canopy. Else, most of the fires are the surface fire. Moving to the Himalayan forest fire mechanism or dynamics, uh, we all know that most of the cases you will get most of the fire in during the pre-monsoon time, and within that pre-monsoon, this is a 30 years climatology where you will see uh, during April and May there is a lack of precipitation or there is a less precipitation, but during that time your maximum temperature and minimum temperature is high, and this is the main windows of for the higher high fire intensity or high fire activities over Uttarakhand and Himachal Pradesh. And I was trying to check the seasonality of the fire during the pre-monsoon. And if you see the seasonality or the peak style or seasonality of the fire is a bimodal peak during the pre-monsoon. The first peak is during the March and April, between the March or March and April, and the second peak, and the reason for the first peak is the higher accumulation of the fine fuel, but the second peak is the reason for the second peak is the increasing dryness and high temperature plus some sort of existing fuels. And I was trying to do some comparison with the decadal change of the fire seasonality and the peak frequency of the fire. It seems like in the second decade, that is 2011 to 2019, the peak get higher, means the numbers of fire is get increased, but the seasonality get narrowed, means within the small time the numbers of fire get increased, or most of the fire find the small narrow time frame. We don't have any fire after that. Mostly the fire season is stopped by the monsoon. If you have monsoon, then you will not find any fire. After monsoon, no, I didn't check that because if I say 10% of the fire you will get during the post monsoon. Yeah, 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 yeah. Oh, oh, sorry. Let me correct. That not the black box. That the the red. Yeah, states only. Yeah. Mm-hmm. You mean the okay, if you clip out the fire points that you get using this, this outline of the boundary, then you can get the number of point, and you just you need to add another layer of vegetation. Uh, Modis, yeah, mostly I use Modis and VISSR. Yeah, yeah, latitude, longitude, and fire relative power. Yeah, Yeah, yeah. You can use any geospatial software, any geospatial software that can do that. Yeah. Anything else? Okay. There is another interesting observation from this seasonality is that from first decade to second decade, the peak time of the fire get delayed, or the starting of the season get delayed by I think 7 or 8 days. If I compare the first decade, that is 2001 2010, and the decade is 2011 to 19, in the second decade there is a delay in the seasonality, or there is a delay in the fire season. Yeah, yeah, yeah. Okay, this is observation. This is observation from Uttarakhand, Himachal Pradesh. According to the research, it seems like it says that first peak is mostly contributed by the high deposit of leaf litters, and the second peak is mostly contributed by the leaf litters plus the high temperature and dryness. Is the representation of the entire Uttarakhand and Himachal Pradesh fire observation time or fire incidence time. 60 is the Julian days. It's starting from March, April, and May. March, April, May, June, 4 months. No, I'm not starting from January. Yeah, around 120. Roughly, it's the first one is the April. Sorry, March. March. Yeah, April last. Yeah, yeah. Uh, next May and first week of June, I most probably. Yeah. This is observation. This is not something that I create. This is observation that I got. Yeah, yeah. That's yeah. Second one. Which one is second one? You mean the okay? Mm-hmm. Yeah, yeah, yeah. Okay, okay. Let me tell you that first peak is that you say that is the observation so the observation from 2011 to 2019, and what I can inform from here in here is that in the second decade or second peak, the numbers of fire incidents are high in small time. That's the explanation that I can see. Mm-hmm. Mm-hmm. Okay, that I have. Just let me go to the next slide. This is also density, but over a different part of the India. Sorry. This is taken from the fire count. This is the number of fire count. Okay, density means yeah, probability density function. Probability density function. Probability density function. Yeah. No, 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 no. This is probability density function. Yeah. Steady. You mean the skewness? Yeah. Simply the probability density function. Yeah. Yeah. Mechanisms are that the first peak is due to the high accumulation of the leaf litters. And the second peak, that is during the June, you have the very high temperature and the dryness that makes that second peaks. Mm-hmm. 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 For 10 years. Yeah, it's consistent. Yeah, yeah. Mm-hmm. Mm-hmm. If I say it's an average representation, so obviously individuals are contributing to represent this average, right? Yeah, I think, but it's not here, but it's representing the similar pattern. Similar pattern. You'll find similar pattern. Mm-hmm. 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 Okay, yeah. I agree. I agree that. Yeah, yeah, I agree because this is average representation of the decade. June, yeah, mid. First is April, yeah. May starting with that the I'm not checking the contributing factors here. I'm just trying to figure out the pattern of the seasonality. I'll come to the contributing feature. Yeah, yeah. Yeah. That's to represent that is there really difference or not. Uh, and I try to do the similar stuff over the into different part of the India. And if I change the shape, if I include in Jammu and Kashmir with Uttarakhand and Himachal Pradesh, you'll get kind of similar pattern as well because mostly Uttarakhand and Himachal Pradesh is dominating in terms of the fire over the Western Himalaya. And if you follow the southern India and central India, you'll find the fire is initiating little bit early. That's a March, and you'll find the peaks are also little bit early. Yeah, this is based on the fire frequency or fire occurrence and date. How many occurrence? Uh, okay, that's possible if you have a land cover image. First, we have a land cover image. We know that which place is agriculture, which place is forest. If I use that filter, I can, yeah, based on that. I have to use that filter to distinguish, right? Yes. Okay. And then I was trying to find out the peak, the peak time based on this incidence time with with a grid size of 25 kilometer by 25 kilometer most probably. And I was trying to compare with the first decade with the second decade, and on an average, it seems like the 7 days and 7 to 24 days delay in the second decade in terms of the initiating the fire season. 2 point. In terms of the, the if I mean, sorry, uh-huh. Mm-hmm. 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 Okay, why it's how it's come the range. If I consider all the pixel is the area, all the pixel. There I was considering the entire Uttarakhand is a one unit. Here for every pixel, I'm trying to compute the same. For that, I'm getting the range. Yes. For each pixel of 25 kilometer by 25 kilometers. Mm-hmm. Mm-hmm. They initiate fast. Mm-hmm. Mm-hmm. I mean to say peak fire means which particular day has the highest number of fire in that particular pixel. I mean to say which particular day have received highest number of fire, numbers of fire within that grid. Okay. Yeah, blue means this is starting a bit early, means like from March. Okay, and not starting is the peak time, which is the peak time of the fire. Means the when I had the highest number of fire activities within that grid size. Mhm. Yeah. Mhm. Yeah. Yeah, it's kind of like that. Yeah. Uh, it's like between February, March, like that. Yeah. There is fire, but that's not the peak time. Here I'm trying to identify the peak time of the fire. But can I use the board if I can? Okay. Maybe it can make you. Maybe it can help you. Uh-huh. Okay. Just give me a second. Might be it can help you. Suppose if you have DOY here and you have the number of fire incidents. Fire incidents. Okay. You have the day of year and which particular day has how many numbers of fire for each pixels. Suppose assume this is representing 1 pixel and I see like 50 and this one is 100 and I see here I have the number. This is the play point or this is a day where I peak day. Yeah, yeah. Okay, if I can explain that pixel one, then that could represent the entire map, right? Yeah, this is how I'm trying to represent here, right? So this is representing one grid where I take down or take the number of incidents for each day, and which day I have received the highest number of fire, and that day I coded with this color. Yeah. Mhm. Okay. Hmm. Yes. Yes. That's wrong. Okay. Uh, okay. Maybe the fire is there. I agree. Maybe the fire is there. I mean to say which date has received the highest number of fire. I'm not saying that after that there is no fire. Might be the fire is there. I'm saying which date has received the highest number of fire, maximum number of fire. Mhm. Mhm. Yeah. No, not for the intelligent. I did it for the 25 kilometer by 25 grid. Mm. Yeah. 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 Mm-hmm. Mm-hmm. The highest one. The other one. I agree with you. I agree with you. Because the Eastern Himalayan one has the unimodal only. But that's the problem with the Western Himalaya because it's a bimodal. Uh, to identify that which particular date or particular times you have the highest number of fire, to understand that what was the the reason behind that. Maybe it's weather, maybe it's some human activities or something else. Yeah. Mm-hmm. 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 Yeah, I agree with you. It's there. It's there. No, fire is there. Fire is there. I mean to say fire is there. The number may be the not that high. Yeah, 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 yeah. Even that graph, this table is built based on that graph. Yeah, yeah. For that, I did the seasonality, right, to understand the or how the seasonal pattern. Now I have the seasonality. Now the seasonal pattern, misleading of what that I have to understand. Okay, in similar way, I was trying to look into the southern India and the central India part using some agroclimatic regions. And you will see the most of the fire you will find over central India and southern India is started from January, February, and it's run up to May or April. And there are changes in terms of the peak fire time over the western plateau hilly regions that get delayed for few days. I think it's 10 to 15 days. The data is not there, but it's around 10 to 15 days delay in the second decade. Yeah. Uh, yeah, because you have the whole spectrum. Mhm. Mhm. Okay, may I? Okay, there the idea was to understand the size of the fire, individual fires, and calculate for each decade what was the average size of the fires for first decade and second decade. And it seems like in second decade, there is just a little bit down in terms of the size of the fire, but the number of the fire get increased, but the size of the fire get down, and the frequency get increased. We'll see that in the next slide. Uh, if you see the same thing over central and southern India, you will see from first decade to second decade there is a down or decline of the size of the average size of the individual fire from north sorry from southern to central India. Only the western plateau hilly regions have some sort of increase in terms of the individual fire size. And then I was trying to check how the what the trend of the fire burn area over from different physiographic regions from 2001 to 2020. And it seems like if we follow the graph that southern India and central India, you'll find that there is a strict increasing pattern of the forest fire and grassland fire. Uh, Following, if you see, but if you see the northeastern Himalaya, there is a declining trend after 2010 in terms of the burn area. And there's another component of fire that is the fire radiative power. As I mentioned the first that vegetation component of vegetation type that's really controls a lot in terms of the initiating the fire or in terms of the catches the fire. One of the catching fire is the how much amount of energy it reflecting. That's fire radiative power, and you will see the highest fire radiative power that is over northeastern Himalayan region because the fuel type is the evergreen needleaf or evergreen broadleaf fuels forest, and its content is huge amount of water, and fuel density is high. That's why you will find the high amount of energy which releasing from that energy or that region. Sorry, fire radiative power, the amount of energy that reflect unit is megawatt. Yeah. I think almost, yeah, yeah. Mm-hmm. Yeah, yeah. Mm-hmm. Mm-hmm. If you see crop fair, the FRP is really low because crop have really less amount of biomass. If you see, uh, okay, oh, oh here, okay, uh-huh. Mm-hmm. Uh, because okay, that could be possible due to the misleading of the vegetation, or sorry, the land cover type. If the land cover type, the classification of the land cover type is not right, that I can't do anything because I am each. Mm-hmm. 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 Discriminating the, yeah, for, yeah, doubtful because land cover can get into 80 or 70% accuracy is there in land cover. Mm-hmm. Yeah, I agree, because if you see the classification accuracy, it's 70 to 80%. So we have to rely on something which will differentiate the land cover types, right? And we really can't do ground based or field based something to map a large area. Mm-hmm. 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 Yeah, that's high. If you see the top one, that forest, that's really high. But in the distribution plot, it's not visible. That I understand. Yeah. But if you do an average or special average, you'll see that. Okay, I can explain this why this 2000, because maybe some pixel which I'm considering here as a crop land, but maybe that's the forest land. Yeah, yeah, because that's misleading of the land cover type. Yeah, 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 northeast. Yeah. Okay, the if you see the forest type, it's evergreen broadleaf forest. It's contain huge amount of the wood density or the fuel density is really high, and it's contain a huge amount of water. And if you burn some fuel which have some sort of water, uh, uh, okay, so that release really huge amount of energy in terms of if you see the density of the fuel, that's high. That's simple. Hmm. Okay, the crop that you see the high, that's maybe due to the those points I consider as a crop, but may not be there. Those are crop. That's the misleading of the land cover type that we are discussing right now. Hmm. High or low? Crop are higher? No, crop are I think lower. Crop and you mean this distribution or this one, the special one? Okay. Hmm. Okay. Yes. Hmm. Yeah. Hmm. 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 Okay, see, there's one more limitation. I think that's I should mention here. That is, we are considering modest Faraday power, which is measured in 1 kilometer by 1 kilometer resolution. And suppose if you have a area where uh, forest fire is there, and some grassland is also there, some sorry, some crop is there, cropland is there, and if that region is categorized as a cropland, but actually that's burning is due to the forest. So if the forest is burning, then you will get a higher energy. But what the land cover type is did is land cover type converted that to cropland. Yeah. Okay, it's modest IGBP classification. Uh, they have they have this some global quality classification or a quality, but not for each pixel. Yeah, the quality, yeah, that is including cloud and all. There are lots of information is there. Means, uh, yeah, even they provide a single unit of uncertainty. How much amount of uncertainty is there in that particular pixel? Yeah. Mm-hmm. Mm-hmm. Agriculture. Mm-hmm. Okay. What I did is I use actually Modis provide annual land use land cover. So for each year of fair analysis, I use that year's annual land use land cover so that I can eliminate that error. Accumulated annual value of what? Of land cover. It's an annual land cover product. Mhm. That based on the um, Modis spectral channel and some sort of indices is there. Yeah. Mm-hmm. 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 That's the annual average. That agree. That's right. Annual average of the reflectance. Mm-hmm. Mm-hmm. Based on the land cover classification of the region. Mm-hmm. 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 Yeah. June. Yeah. That's the annual classification. That has. Yeah. All right. Oh, thank you. Okay, and then I was trying to connect how this burn area is connected with the regional regional climatic condition. This one is the analysis over Uttarakhand, Himachal Pradesh, and it seems like if you see the last 20 years average burn area and the maximum temperature and precipitation, you will see two different peaks as well, and there is a quite good agreement with the maximum temperature and precipitation with the burn area, and it seems like it 1 degree of temperature get increased, then it might accelerate the burn area of 510 square kilometer over Uttarakhand, Himachal Pradesh. But in terms of the precipitation, it seems a little bit low in terms of contribution. And I was trying to connect with the global regional, sorry, global climatic indices. One of those is Nino 3.5 is the indicator of the global sea surface temperature condition, which represent the which is El Nino or La Nina, and there's a really good connection with the Himalayan forest fire anomaly and the Nina 3.4. It's quite positive relation with the Nina 3.5 means sorry 3.4 means if you have a higher value then it's El Nina, if you have a lower value then it's the La Nina, and it's quite positively associated with the Himalayan forest fire anomaly. All right. Then the idea was to model the fire occurrence, that if I have a fire occurrence, what are the contributing factors there, and uh, what are the contributing factors there, and could we expect or could we model something to explain that that particular location will going to get fire occurrence or not based on the probability. Uh, there are few, weather factor and environmental factors which really controls the fire environment, including temperature, elevation, water deficit, vapor pressure deficit, and all. And explaining that using a machine learning technique or machine learning supervised machine learning technique, it's possible to explain the fire incidents as a classification problem, and try to rank them based on the contribution in terms of initiating the fire. And it seems like the maximum temperature, elevation, minimum temperature, water deficit, vapor pressure deficit, those are the component which highly contributing to initiate a fire. And another experiment was to check that how neighboring regions is, neighboring regions has a control on fire initiating in a area or not, including that environmental condition of that particular regions and in, additive of its neighboring regions. And it seems like along with the condition of that particular regions, the neighboring region has a really good contribution in initiating the fire and spreading the fire. If I say the the average of the entropy and average of the 3 by 3 grid, means if I say this experiment was done in 1 kilometer by 1 kilometer grid, and it seems like the neighboring regions or neighboring regions elevation, temperature has a really good control to initiate the fire, or to decide that fire will initiate or not, or that the fire will spread or not. Yeah, this is the association between the actual fire occurrence and the predicted the probability of the fire occurrence. And you will find maybe random forest and XGBoost are playing really good in terms of the predicting the probability, higher probability of fire and its actual location. And then I was trying to project that for the future, from 2000 for 2030 and 2040 and 50, and it seems like the fires, the probability of high fire is migrating towards the higher elevation region. And I'm expecting, or we are expecting from this model, from this analysis, that over the time for next coming decades, the numbers of fire occurrence over Uttarakhand and Himachal Pradesh is going to migrate towards the higher elevation region. Mostly it was between within the 2500 meter, but it seems like with the increasing temperature, it might migrate to the little bit of higher elevation regions. And this is another experiment to explain the anthropogenic fire and natural fire over entire India. The idea of an anthropogenic fire or a natural fire, if you have a large fire, then that mostly, is fed by, or that mostly supported by the environmental condition or natural condition. And if you have a very small fire, then you can consider that mostly initiated by human activities and the environmental condition that didn't support to grow it. And to do that, the size of the fire is really varies from very small number to very high number. And it's very difficult to explain that sort of range using a single model. For that, we need to segregate, or we need to segment the data based on the distribution of the fire burn area size. To check that, I apply a segmenting approach, that how many numbers of model I need to explain this range of the burn area data over entire India. And the first row that you'll see without adopting any clustering approach, but the second, the last row that you see is the, if I adopt a clustering approach and the optimum number of cluster I've decided based on the, I just start, adding the number of cluster or number of model that I need to explain this data. And once I'm trying to check the RMSI. If the RMSI is declining, then I'll keep adding the clusters. If it's not declining or it's get increased, then I'll stop there and I'll consider that number of cluster is the optimum for this data set. And if I found that 17 is the optimum number of cluster for this data set to explain the burn area as a function of environmental and few human parameters. And again, using the social science pathway projected climatic data, try to project the burn area for 2030, for 30 and 50. And you will see we're expecting that over central and southern India is going to get higher amount or higher number of activities from with the coming decades with increasing the temperatures. And the next project was to estimate the forest fire emissions from the fire over Himalaya. And most of the global fire emission data sets are in coarse resolution, maybe that 1 kilometer, or sorry, maybe that more than 1 degree, that is 100 kilometer. So it's very difficult to use those data for any modeling. For that, I was trying to estimate the emissions from the forest fire in every kilometer grid size. Estimating forest fire emission any emission from forest fire, there is a two approach. One is the bottom up approach and there is a top down approach. What is the bottom up approach? That you have the area of how much area that you burn and how much biomass that you burn. If you have that information, what you need is what is the emission sorry what is the combustion efficiency. Means if you have a 1 kg of biomass, what is the capacity to burn that 1 kg? Will it burn the entire 1 kg, or how much fraction of that biomass could burn? And after that, for every emission factor, you need the emission factor that get from the different experiment, or the chamber experiment. And after that, I compute the emissions from entire Himalaya from 2001 to 2020 in 1 kilometer resolution using Modish Barnier data and biomass data that I got from Yana Max Planck Institute. And then to compute the combustion efficiency, I use a dynamic combustion efficiency using the earth observation data to understand how much amount of moisture is there, because moisture is the controlling factor to define the combustion efficiency, or how much fraction of the biomass will burn out of that existing biomass. The another thing is the top-down approach. That is, if you have a observation, or if you have a measures of the amount of emission that you have in the atmosphere and how much amount of emission that's added by the fire, if you subtract that, you maybe find some sort of amount of emission that you get. But the uncertainty in that approach really high. That's why I try to go through this bottom-up approach, that where I have the amount of area burn and some sort of biomass that I have burn, and combustion efficiency and emission factors. And the left-hand figure that you see the average of carbon dioxide emission from forest fire over from 2001 to 2020. And there's interesting thing that you'll see in the burn area, that after 2010, there's a declining pattern of the burn area if I consider the entire Himalaya. And if I only consider the northeastern Himalaya, you'll see a sharp decline of the CO2 emission from the forest fire. That's due to the declining trend of the burn area of northeastern Himalaya. That's the good thing, that over northeastern Himalaya, we are controlling the uh, area of burn or the frequency of the burn. And this is the average spatial map of CO2 and CO2 and CO. And you'll find the higher number of emission, or higher amount of emission over some sort of central Himalaya and most of the central Himalaya. Interestingly, these emissions are distributed over, or this depends on the forest type or the plant functional type, and over these three different Himalayas regions, you'll find mixed forest, deciduous broadleaf forest, and deciduous broadleaf forest and evergreen broadleaf forest are the main contributing in terms of the burn area. That's why those forests have the higher amount of emission. And to validate this data set, or to validate this production, I was trying to compare with a global recognized fire product, that is the GFAT, that is the global fire emission data set. But the demerits of this data set, this is available in 25 kilometer resolution. But the product that I developed, that is in 1 kilometer resolution. But still, I can do some comparison if I consider the the entire administrative regions. And it seems like there is a really good association with the with my major emissions and that global product that's given. Only and another observation from this comparison is that the global fire emission data that we are getting, that's kind of underestimating the emissions that we are getting from the fire. And then I was trying to see what is the wind vector trajectory for March, April, May of 2010, 16, and 18. because 10 and 16 was a quite high fat period, and 18 was kind of moderate period. So I was trying to see the average wind projection of those time or those months, and it seems like after hitting the Himalaya, winds are projecting towards the little bit of south and southeast. Then we might draw some conclusion from here that the emission that we are getting from the fire, that's that's dispersing towards the Indo-Gangetic plain and the lower part of the Himalaya. And to exactly understand the path or the projection of the that emission parcels, we choose few points where large number of large fire activities are have gone, and try to do a four trajectory for few days, and it seems like it's similar. It's following like the similar wind projection is like following towards the east and southeast region, which is one of the Indo-Gangetic plain, which is the the densest population regions of the global of the globe. And then there's another experiment I was doing with to connect with the number of fire intensity or burn area and the emission that measured by the satellite sensors. And though it's really difficult to say how much amount of emission that you are getting from fire using the satellite imagery, but we can find an association between both. And you will see there is a really strong association with the burn area and NO2 burn area and CO and DCOC and sulfur dioxide. Then another work was that if the fire happened, how much amount of forest is getting degraded, or really it's getting degraded or not, because most of the fire are surface fire. Sometimes it's not impacting the trees, and we found out from this satellite-based measurement that analyzing 6 year or 7 years of analysis, that around 5 to 9% of the burn area is really impacting to degrade the forest, but rest of the area is not impacting that much to immediately degrade the forest, but it takes time to degrade. If I conclude here is like 5 to 10% of burn area that degrade the forest every year. Next, I'm trying to go to my next part of the talk, that is the how this climate cycle and fuel cycle controls connect with each other, and how we can exploit this cycle to understand to do some fuel management to control the fire. There is the Indian vegetation system or vegetation or forest system is depends on the monsoonal cycle and vegetation cycle. If you start the pre-monsoon, post-monsoon, and we have a winter, and there's the phenology is connected with the wind, is connected with the monsoon. If you have a higher amount of precipitation, then you will get much more biomass for the next season of the fire, and you can identify which regions has the highest amount of biomass if you just subtract the how much amount of the greening was there during the peak greening time, and how much amount of greening is there during the leaf set time. And if you subtract that, you will find how much amount of leaf set is done, and which is basically the immediate fine fuel to initiate the fire. So we can take the advantage of that coupling of the climate and vegetation cycle, because the fuel load that is complete depends on the vegetation cycle, and vegetation cycle is depends on the climatic cycle. And that vegetation cycle, if you track that vegetation cycle, and we really can identify the which regions has the highest high number or high amount of biomass, the flammable biomass for the next fire season, and we can directly give that information to the local fire authority to do some fuel management. Like I'll say about the fuel management techniques, but we can identify the which regions has the higher amount of fuel for the next fire season. And there are some fuel management or fuel management techniques. One is the prescribed fire to just thin the fuels. Suppose if you have a very huge amount of dry fuels, if you identify from the satellite imagery, then you can direct to the local fire forest authority to thin that fuel, or to do create some break so that the fire will not spread much. For that, you have prescribed fire burns. For that, you need a fire window and which regions you are going to burn, that you have to decide based on the local geography and weather condition. And then coming that thinning of the fuel. Suppose you are not able to you are not able to cut all the trees. So what you can do is, if you have a very dense fuel, then you can cut few of the trees and take them out. So in that way, you can thin the fuel, and the risk of the fire spreading or risk of the higher intensity fire, you can drop that, or you can make it down. And fire break, you might create some fire break that if you have a very plain area, or if you have a there are some natural fire break, like if you have a very high slope, there's natural fire break. Else you can create fire break of some meters. It depends on the geographic condition. Early detection response, if you are trying to do some modeling, is that possible? That's possible to predict that which regions are going to get the fire for the next seasons, in using the historical fire observation and connection with the environmental condition and anthropogenic condition. These are some of my field photographs to just characterize the fuel load, that is the initial fuel load, or that is the leaf liters, and how people are, local forest fire authority trying to put off the fire, and what's the impact on the trunk. I think you guys know all this. And these are the reference that I took to, make this presentation or make the story. And thanks for hearing me out. And if you have a question, we can go back and we can discuss it more.
Question?
Thank you. Mm. Okay. Hold on. If I can show that. Okay. What are the variable that I took? Mm, Let me miss that content to upload here. Maybe if I can. Could be some of here. Yeah. Can you see this graph? So what are the components that I took to explain the burn area intensity or burn area? That is the maximum temperature, minimum temperature in every 1 kilometer grid, and population density, because that's the component to explain what sort of human activities or what sort of intensity of human activities is there. And then latitude, longitude to explain the location. And then global human modification, this is another data set. This is it's include human population, as well as how much that particular region is converted by the human activities. Like it's include construction, railway, everything, means whatever the human footprint it could consider, and precipitation. So this sort of component that I took to explain, you can add, based on your study area, you can add few more, or like, I go to my, hold on, let me take you to that slide. So here you have much more environmental components, or which considered as explanatory factors or as a explanatory component, that fire incident, whether the fire incident will happen or not. That is the human relative humidity and uh, wind and solar radiation, roughness of the topography, population, slope, the aspect, roughness. So you can add, if there is a really, if there is a physical connection with that fire incidents, then you can include that, and you can check that really is that any connection, or is there any impact on fire initiation or not, using different statistical techniques. Yeah. Okay, future projection. Suppose for future projection, the static data sets are like the elevation, geographic condition, these are static. I can't change those, right? I don't have population projection data set. I can't change those. But what I can change is the climatic component. Those are the dynamic data. I have the projection of climatic component. Yeah. So I use the same static data set, that is geographic data set and human data set, but the climatic data has changed. It's around 3,000 meters, 3,000 to 3,500 meters. But it seems like we are going to get, or the fire are migrating towards the higher elevation. If you see the temperature is also increasing towards the higher elevated regions. And that could be another reason that we are going to get higher number of fire activity in the higher elevated region. Now it's mostly between 1,800 to 2,500. Yeah, 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 yeah. I can go back. Yeah, yeah. Okay, this is a schematic, representation of the vegetation cycle. That there is a vegetation cycle which follow the monsoonal cycle. Uh, Forget about the colors, okay, because I took it from somewhere. But you can understand this one, that you have a greening cycle. If I start from the monsoon, yeah, and this is the post monsoon. So this is the time for the leaf shedding, and uh, if I subtract the amount of the peak and the value of the greenness, then I can find the how much amount of leaf is shedded, and that's waiting for the next fire season.
Okay, Somnath, can you uh, comment on how you differentiate between the natural induced fires and the anthropogenic one?
Okay, the idea is 90% or 99% fires are initiated by human activities, but that fire will spread or not, that will be decided by the environmental condition. If the environmental conditions support it, then the spread will be high and the burn area and intensity will be high. So if your burn area size is large, then I would say that's natural fire. Okay. And if your burn area is small, then I'll say that's the only human fire. There are some categorization, there are some standard categorization, like people used to say if the burn area is more than 1 square kilometer, then you can call it as a natural fire. That depends from area to area. Like in Canada, they use I think 1 kilometer. In USA, it's 1.5 or 7 kilometers. Yeah. Mm-hmm. Uh-huh.
Yeah, because see, if there is anything in the Himalayan region
Mm-hmm.
and there's some fire induced in the March April, the environment in the fire season,
Mm-hmm.
but it was induced by anthropogenic activity.
Yeah, I accept that all the fire are initiated by the human activities. I accepted that, but
I mean, again, that's a very very general statement. That's also not true. There are many fires which are
yeah.
natural,
Mm-hmm.
but what he's saying is that even human induced fires
Mm-hmm.
can have a larger burn area.
But who will support if the environment, if you have a high moisture, if you have a very low temperature, if
Okay,
you are
so
getting precipitation.
okay, so
Uh-huh. If, okay, if you mean to say natural initiated fire, are you saying natural initiated fire? That's
is naturally induced fire, and another terminology you have used is anthropogenically induced fire.
yes,
Induced fire. That counts for initiation, not
yeah.
spreading.
Spreading, I don't think human can
The
control.
reason you are giving is for spreading. It is
Yeah,
not
yeah,
for initiation.
yeah. Region is the spreading.
Okay, and another thing you said about forest degradation.
Mm-hmm.
Now, how do you classify that the fire is degrading the? I mean, it's contributing to the degradation because see many activity. I mean, there have been tribal uh, areas. I mean, there have been tribal people who regularly, go on and cut the. I mean, do some anthropogenic forest fires,
Mm-hmm.
but then they are controlled and they actually help rejuvenate the forest.
Mm-hmm.
How do you say that a forest is being degraded because of the fire?
Okay. So the idea is I have the burned area. Okay. Suppose I have last year, suppose the area get burned, and I'm trying to check for the next year that what is the response of vegetation. If I compare with the prior year is same, then I say there is nothing get burned or no, sorry, nothing get degraded. If I see there is a very low peak of or there is no response of vegetation, then I could say that region get degraded or that vegetation get degraded.
Okay. So if I understand correctly, what you're saying is you compare the forest area,
Mm-hmm.
forest area cover
Mm-hmm.
in 2011
Mm-hmm.
and comparing it with 2012.
Mm-hmm.
If the area is same, you're saying it is okay. If it is degraded, you're saying that this is because of fire degradation.
Okay, suppose assume this is a vegetation index or vegetation response. Suppose I have a fire on 2010, and during the peak time,
What's on the y-axis? Sorry,
sorry,
what's on the y-axis?
it's a vegetation response, vegetation index. Okay,
NDVI or EVI or
assume it's a
anything.
cleanness index. Okay,
NDVI,
NDV.
EVI, anything. Okay.
Suppose if I said in 2009 it was 0.6 during the peak time. 2010 has a burn area over that particular region, or same pixel. And if I check in 2011, the same during the peak time, if I find that if it's close to 0.6 or 0.5, I say it's not get degraded. But if I find it 0.2, I'll say the fire, fire induced that to degrade that vegetation of that particular pixel.
But that reduction could have been because of anything. It could have been because of human encroachment. How do you say that this is because of fire?
Because I took the fire pixel only. I took the fire pixel only that get.
No. So this
Yeah,
is
yeah, yeah, I understand. You mean to say after fire that human could, deforest that, right? Or if the deforestation is there. Ah, okay. That's difficult to say. But there is a way to distinguish between the deforested land or the degraded land. And the indices that I use, if you see that indices, this ND normalized degradation fraction, uh, using the scale of this indices, you can identify that this region is deforested or degraded. It has a scale from I think -1 to +1, and if it's deforested, then you will find the close to -1. But if it degraded, it will be a little bit higher than that.
can vary, right?
Rejuvenation is really a hard word to say, because if you have a forest, then it will take minimum 5 to 6 years to rejuvenate. If you have a grassland, subland, maybe it will take 3 years or 2 years.
Yeah. So it's hard to say whether things have contributed to degradation as such or not.
Yeah, you have to take continuous observations. Yeah, you can do that. Oh, thank you. Um, Thanks for hearing me out for 1 hour. Okay.